Okay, today's concept is going to be about angular momentum, and there'll be later videos that talk more about this, but the definition of angular momentum is that it is the cross product of the radius and the momentum. And this is, yes, the regular momentum that we looked at before. So because it involves a cross product, let's review cross products. So if I have two vectors, vector A and vector B, and there's an angle between them from A to B of angle theta. The way to calculate the cross product, if I know the magnitude of A and B, that is A cross B, is going to be equal to the magnitude of each times the angle between them. So it's A times B, these being the magnitudes, times the sine of the angle between them. Now the direction of it isn't provided by this. This just gives you the magnitude. The direction, of course, would be given by the right-hand rule. So I would point my fingers along the direction of the first vector, in this case that's A, and then I would want to hold them in an orientation so I could bend them towards B. So I hold them downwards so that I can bend them from A to B, and of course my thumb points down. So the cross product of A and B is going to have this magnitude, and its direction is going to be into the board, away from us, right? Now that works great if I actually know what the vectors are in terms of magnitude and direction. So if they were graphed like this is an adequate way to find the cross product. But sometimes we're provided with the vectors in component notation. So the definition of A might be equal to AI, or A1 in the I hat direction, plus A2 in the J hat direction. And vector B might be indicated as B1 in the I hat direction and B2 in the J hat direction. In which case I might not want to go through the task of graphing them. I might want to just be able to work with them directly in their component notation. And that's fine too, because there's a way to find the cross product without necessarily having to see the vectors. And that is, we find the cross product of multi-dimensional vectors provided as their components by using the determinant of their coefficients. So A cross B is also equal to the determinant of the matrix formed from their coefficients. So that would be A1, A2, B1, B2. And then to find the determinant, it literally is the cross product. You're going to take the product of A1 times B2 and then subtract the other cross product, B1 times A2. And this actually comes with a direction too, because these guys are both in the IJ plane. That means that the direction that's perpendicular to the IJ plane is the K plane, because I is the x-axis and J is the y-axis, and the only axis perpendicular to both of those is the z-axis, so that would be the K direction. I don't know whether it's the positive K hat or negative K hat, but this product will tell me. That is, when I work this out for these two vectors, this will either be a negative constant or a positive constant, but that will be in the K hat direction, and that will tell me exactly how the vector that represents the cross product of these points, all right? So if you have them in magnitude direction form, then you can go ahead and graph them and find the cross product by finding the angle between them. But again, that won't tell you the direction, just the magnitude. And if you have them in component notation, you can find the cross product directly, and it'll not only give you the magnitude, which is this quantity, but it'll tell you the direction, whether it's pointing into or out of the board. Now, this works great for two-dimensional vectors because the cross product, or the determinant of a 2x2 matrix, is very easy to find. It gets a little bit trickier when it's a set of 3D vectors. So let's do one of those. So I'll define the two vectors as A, which is A1 I hat plus A2 J hat plus A3 K hat. And A1, 2, and 3 can be really any values. It just determines the direction that the vector points in the three spatial directions. And then B will be B1 I hat plus B2 J hat plus B3 K hat. Now the cross product in this case is going to mean finding the determinant of a 3 by 3 matrix, not a 2 by 2, and it's a little bit more involved. Here's what that looks like. So we've got A cross B, and then we've got to form the matrix we're going to take the determinant of. The top row is I, J, K, and then the next two rows are the coefficients of A and B. Always A on top and B on the bottom. A cross B implies that the middle row has to be A and the bottom row has to be B. So it's A1, A2, and A3, and then B1, B2, and B3. And now we're ready to go ahead and do the cross product. These are all unit vectors too, I, J, and K. Okay, to do a 3 by 3 matrix, it's really just taking three different 2 by 2 matrix. It's called the elimination method, and basically we're going to begin with I, and we're going to eliminate all of I's row and column. Okay, so with the row and column gone, what's left is these four, A2, A3, B2, and B3. We're going to do the 2 by 2 cross product of that times I. So it'll be A2, B3 minus B2, A3. And then all of that is in the I hat direction. So that's in essence the X component of the cross product of these two vectors. I can go on and find the other two components. The middle term J has an extra negative added to it. So you always put minus. It basically goes every other term is minus. So if we were to do a 4 by 4, this one would be negative 2. But with a 3 by 3, there's only one negative, and that's the middle column. So negative, and then we do the same thing. I eliminate this row, I eliminate this column, and what's left is A1, B3, B1, A3, and I do the cross product of what remains. So it's A1, B3 minus B1, A3, and that is times J hat. And then plus, and we do the same thing with K. I eliminate K's row and column. What's left is A1, A2, B1, B2. So it's A1, B2 minus B1, A2. And all that's times K hat. And so if you have a vector that's 3 by 3, and you want to take the cross product of it with another 3 by 3 vector, this is how you do it. That's how you do the determinant of a 3 by 3 matrix. Some of you might have seen this in your math class. Certainly the students in my differential equations class, we did a bunch of linear algebra this year and covered this. But for those that haven't done matrix determinants, it's not really all that difficult. It's a little bit procedural and there's some algebra to it, but that's how you're going to be able to find the cross product. And as I said, it's important for today because finding angular momentum is a cross product.